So the next presentation will be by Roger Barlow from Huddersfield University. And he will talk about accelerator development for ADSR. So please, Roger.
Yeah, it's nearly lunchtime. I really appreciate you all staying in just to hear me. And I don't anticipate many questions at the end. So I want to talk about the requirements of assuming that your reactor needs an accelerator. What sort of accelerator does it need? Much of this, of course, has been gone over by previous speakers, inevitably, but I still have some other things I think need to be said. To compare what we want with the performance of current and proposed systems, and then to look at just two new proposals. One is the D-less cyclotron, which Pierre already referred to and kindly let me talk about, and the other is a proposed non-scaling FFAG solution. So, protons are the obvious beam particle. There have been some studies of electron ADSRs, but they don't really get anywhere. There is no real advantage for ions. This is the canonical picture showing that 1 GeV is the energy you want. This, as it happens, is an MCNPX simulation of the number of neutrons per GeV as a function of proton energy, and it plateaus at around 30, maybe a bit more, at 1 GeV. Above that, 2 GeV gives you twice as many protons, etc. But it is probably easier to make two 1 GeV protons than 2 GeV protons. So, what power do you need? Take some typical numbers. Suppose you want a gigawatt thermal power, and the K has become beta for some reason I don't know. But the reactivity is 98%. Then, to get 1.2 megawatts, you need 10 milliamps of protons. You put in the current, multiply by this number, which might be around 30, depends on your target and what have you. Divide by a number which is about 2.5, which is the fraction of neutrons that actually go on to create a fission. Then you have the chain reaction factor. Then you have perhaps 200 MeV per fission, and that gives you the final answer. So, why have I taken 0.98? Because obviously, if you could go up to 0.99 or 0.995 or 0.997, then you could reduce the power of your accelerator and make life a whole lot easier for yourself. It's caution, and there's one point I want to remind people of here, and that is the so-called protactinium problem. When your ADSR is running, you have a dynamic equilibrium in which thorium is turning to protactinium, which is turning to uranium, which is fissioning to fission products. Fine. You want to stop. So you hit the big red switch, and the accelerator stops, and the fissioning stops. Fine. All you have to handle is the decay product heat, but you're prepared for that. So the third stage of this chain stops, as does the first stage. But the second stage continues because it's a beta decay, it's not fueled by neutrons. So after you have switched off your accelerator and you walk away from it, the uranium-233 concentration is building up and it is getting more and more critical. And you can't measure the criticality because your accelerator is switched off. So you think it's sort of just doing nothing, but really it is building up its activity. And the extent to which this happens over a period of a few times 27 days clearly depends on the design, but the ones I've seen raise it by about 1%. So if you've got a beta of above 99%, then you don't have a deterministically safe reactor which can never go critical. You have to rely on control rods or whatever. So that's why I've chosen 0.98, but you can choose whatever number you like. The answer comes out in the megawatt region. So if we look at PSI, I've taken a current of 2 milliamps. I have heard higher numbers, but this is the number on your website. SNS runs at 1 GeV, the canonical energy. Mirror, ISIS, and PSI have done sort of, they're constrained by history, they're constrained by costs, they're getting as close to 1 GeV as they can. Why the Chinese SNS Stage 2 and the ESS run at a higher energy, I am not quite sure. You'd have to ask them. I think it's complications due to space charge and losses. So the 1 GeV, a few milliamps, a few megawatts. And we are not there yet, but these machines are getting close. So they're close in power, but they're not close in reliability. At one point, there was talk of 3 trips per year, which was over cautious, and the DOE white paper has revised this upwards. Hamid's numbers are more than this, but they are still far, far more demanding than anything that's been achieved. Carlo Robbia said on Monday that this was a solved problem because there had been a machine called LEP, which was a reliable machine. And this is bullshit. I'm sorry he's not here. It is dangerous bullshit. LEP was a magnificent machine, and a credit to CERN, but while Carlo was in the Director General's office, at this end of the ring, I was at the other end of the ring on the Opal experiment, miles from anywhere, 100 meters under the ground, and I spent many, many, many hours in the experiment control room not taking data. Because read the logs, beam lost, operators say no beam before 0800, high voltage trips, vacuum problems. Of course, I spent many happy hours taking data, and I think on average, I probably spent more time taking data than not taking data. So it was a reliable machine from the particle physics point of view, and it was up more than half the time, which is great. Magnificent, and I am privileged to have worked on it. But it cannot be used as a prototype for a reliable machine. We have to think in an entirely new and different way and be prepared to spend money on things that may never be used. Some of these things have been mentioned. In particular, I want to point out that an important part of reliability is maintenance. Inspection and maintenance, you have to take your machine down and replace all the things that are going to break down because of heat, radiation, what have you, and you have to replace them before they break down of their own accord. And it's not just a question of switching it off and going in. You may have to wait 24 hours for the active copper to cool down. You may have to wait for some cryogenic components to warm up before you can look at them. So there's a big inspection and maintenance bill. Wouldn't it be nice if instead of just having an accelerator, you had 2 accelerators, and you could be running one while the other was under maintenance? Or even better, if you had 3, because then, since we're dreaming, let's dream of 3 accelerators. You have 2 normally running and 1 under maintenance, and if one of the 2 develops a fault, then the other one can handle at least part of the load and keep the reactor running. And I would say that the cost of a cyclotron-like cyclic accelerator is considerably less than the cost of a LINAC. One could conceive of a reactor with 3 sort of super PSI machines around it. I can't conceive of a reactor with 3 super ESSs around it. So, as we move from reactors which are demonstrators, and for a demonstrator you want something which you know will work, so you want a LINAC, to something which is commercially viable, something which has to remain up and on air and running not just for technical reasons but for commercial reasons, because if your power supply, if your power station drops out, that makes you very unhappy with your consumers. We want to think about not just LINACs but cyclic accelerators. So one of these options is Daedalus, the Daedalus machine. Daedalus is a proposed decay-at-rest experiment for delta CP at a laboratory for underground science. Fine. delta Cp is an angle in the neutrino mixing matrix, and measuring it is an absolutely crucial next step in understanding the Standard Model and how we got here after the Big Bang and everything. So it's very, very hot science. It does this by looking at the oscillations from muon antineutrinos into electron antineutrinos. And so you take a source of muon antineutrinos, which is just decaying mu pluses, and you look at the formation of electron or positron neutrinos at various distances. The obvious way to do this would be to say, I have a source, and then we'll put some detectors at different distances. But the detectors you need for neutrinos are so big and enormous and costly, it actually makes more sense to have a detector and sources at various distances. So this shows a near, medium, and far accelerator source for one detector. The near one is 1.5 kilometers away because it's on the surface and the detector is underground. They're actually making mu pluses rather than neutrons, rather than spallation neutrons, but they're still basically a big proton machine with a heavy current banging onto a target. So, a proposed way of doing this is the D-less superconducting ring cyclotron, which is making 800 MeV protons through H2+. H2+ was mentioned earlier. You do have to listen very hard to realize that the 2 is a subscript, not a superscript. So, this is described in a recent presentation at the Cyclotrons 2013 conference in Vancouver, and if anyone has questions, then Francis Mayo is in the audience, and I'm sure we'll be happy to answer anything difficult. H2+ up to 1.6 GeV, it's then stripped by passing it through a foil, giving you half the energy going to each proton. You get 800 MeV protons. This is the outermost orbit at the top energy, 1.6 GeV, and there is a foil here. At this point, the protons realize they're protons and not H2+. They therefore bend twice as much and come out through this channel here. And as was said earlier, that is, that's not simple, but we think we can do it. The H2+ has not been used as much as H-, but it's got lots of advantages. Its binding energy of those two hydrogen atoms is 2.75 eV rather than 0.75 eV as is the binding for H-. The problem with H- is that if you want to bash it around, if you want to accelerate it quickly, if you want to bend it through high magnetic fields, then it's, your proton wants to go one way, your electrons want to go another. It's quite easy to split it up with that lower binding energy. H2+ is much more robust. It also reduces space charge, which is good. The disadvantage, of course, is that you need stronger magnets because you've got more mass. And it also needs a better vacuum because if there are any residual gas molecules around, it tends to snaffle the electrons off them and turn itself neutral. The source, there is one in existence built at Catania, which is perhaps adequate. Other possibilities are under study. It's a matter of getting a big enough current out of the source. We need 50 milliamps because of the phase acceptance, and you've got to get that current as H2+ rather than any other H+ or what have you. Tests are underway and work is being done. Then it goes to a first stage injector, the D-less injector cyclotron, which takes the H2+ from the source and takes it up to 60 MeV. This is a a more simple four-sector cyclotron, conventional magnets rather than superconducting. So the injector is fine. The main cyclotron, the 8-sector, the 8-magnet solution which Pierre showed, the problem was that it didn't leave enough room for the RF between the gaps. So we've now gone to a 6-sector solution. There will be 4 copper cavities in a sort of St Andrew's cross in 4 of the 6 gaps. It may be possible to add more, and as said earlier, extraction is by stripping. And the stripping itself seems to be fine. The magnets are quite big and hairy, but they're no bigger and hairier, well, not much bigger and hairier than the Riken superconducting ring cyclotron magnets. So the sort of thing we are trying to do, the parameters are credible. And they have been modeled quite extensively in ANSYS, looking at stresses, strains, thermal, heat coming in, cold going out. A lot of detailed work has been done on this. The lattice looks nice. The top left shows the isochronicity, so the time for each orbit is the same to within pretty much one part per thousand, which is adequate to run, and the navigation through tunes is not problematic. So that's where the designs got to. There's detailed designs on the magnets. The simulations are now being done using the PSI Opal code, which includes the effects of space charge. But we're not expecting any unpleasant surprises there, because we did the same for the 8-sector design, and that was fine. The injector cyclotron could, on its own, provide an interesting physics experiment by making neutrinos from a lithium-beryllium target, which can be used just near a large detector such as Kamiokande, which will provide a definitive answer to the presence or absence of a 4th sterile neutrino. And it could be that we can proceed in stages. We are already working on the ion source. If we get the ISODAR experiment approved, then we can build the injector, and then beyond that, there is the dealer's machine itself. So this seems to me like a case where there are people, we really, really want to measure delta CP. We think this is the way to do it, by appearance of electron neutrinos in oscillations, and the particle physics is driving the technology. So that when our grandchildren are being asked by the media, why should we spend all this money on science, as I'm sure that debate will not have concluded by then, they will be able to point not just to the World Wide Web, which will probably be obsolete by then, but they'll be able to say, don't you know that all these accelerators that we use in our power stations were originally developed by the particle physics community? And people will not believe this. So the second solution is the FFAG. This actually shows 2 FFAGs. They look real enough to me. These are in Japan. The point of an FFAG is it's a bit like a sector cyclotron, but the field increases as you go out in radius. Not just by a little bit to keep the timing right, the field increases by a lot. So it looks to us like a cyclotron. It's just a collection of DC magnets, but the particles see it as a synchrotron, because they move from a low field region on the inside, sort of this bit, to a high field region on the outside. And if that's not confusing enough for you, I have met FFAG experts who say, well, the way to understand an FFAG is it is basically a LINAC rolled up. So it's all things to all men. The fact you've got an increase in the field means you've got a gradient, which means you've got a quadrupole field, which means you've got focusing in at least one direction. And by providing counterbends, in which the field goes the other way, you can get the opposite gradient. So you have strong focusing. This was invented in the 1950s and abandoned. I think it's fair to say it was abandoned because it lost out to synchrotrons. And that is not just because synchrotron is a much better and sexier name than FFAG. It's because the dynamic range of an FFAG in energy is fairly small. You've got a factor of 2 or 3 in magnetic field between the bottom and the top. At low energies, that gives you a factor of 4 or 9 in energy. At high energies, it gives you a factor of 2 or 3. Whereas a synchrotron, you can ramp up the magnets over a factor of 40 or something like that. It was abandoned. It was revived in the 1990s with the appreciation of 2 things. Firstly, that you can get cyclotron-like currents, and they can run CW. It depends on the particular machine, but you can have a CW FFAG, and that's what we would hope to use. But it has strong focusing like a synchrotron, and it also has fast acceleration. Okay, that's the ordinary FFAG. The non-scaling or NS-FFAG has another wrinkle. Your usual FFAG, the field varies with R, but it varies slowly, like some power of R. And the reason it does that is that ensures that during the acceleration of the particle, as it moves from the inside to the outside, the optics does not change, the focusing and the bending. It's like if you have a synchrotron and you have the bending magnets and the quadrupoles coupled to the same power supply. So the optics doesn't change, that means the tune doesn't change, that means you can set the tune to something safe and non-integer and it stays there. For the non-scaling one, you throw away these requirements. That means the tune will change, that means that resonances cannot be avoided, which sounds like a recipe for death. But the argument is, if your acceleration is fast, you move through the resonances quickly, and they don't hurt you. So we built another real machine called Emma to test the idea. This is a non-scaling FFAG. Okay, it is slightly complicated. There are 84 magnets in there, in pairs like that. Its original name was the electron machine for a muon accelerator. But when we were trying to get money for it, we renamed it because we didn't want people to think that this, we were saying we were going to use it to cure cancer and save the planet and everything. We didn't want them to think that this was just particle physicists trying to get another of their toys funded. So it worked. We accelerate and store electrons. 20 MeV electrons, you can't do anything with that, but it's the principle of the thing. Another nice thing this showed is that you don't just accelerate in the ordinary way by oscillating round synchrotron oscillations. There is a so-called gutter out here in which acceleration is fast. Just to show you that this data is real, this black line here is completely forbidden. It's not supposed to happen, but it did. So, that was 20 MeV electrons. For protons, we have designs. Important disclaimer, this is a map from Carol Johnston, who gets any credit. I run some tracking through it, and anything you don't like about it is my fault. Don't get back to her. So this is a field map, about 5 meters in diameter. As you can see, there are 6 big bending magnets and 12 small counter-bending magnets. And if you go outside of the bending magnet, the field increases by quite a lot. You get the effect both of the extra length and the extra field. And the counterbend is very small, so you don't get much effect, but there's a big gradient. You get reference orbits from this, and this goes from 100 MeV in the middle out to 1 GeV at the outside, very nicely. And the acceptance is nice. I put in a spread of 10 centimeters and 50 milliradians around the reference orbits at the inside and the outside, and they're still inside. This is another nice feature of FFAGs. They have a wide acceptance, which means you don't get much in the way of losses from them. The period is not completely flat, but fairly flat, considering, which is probably enough to enable serpentine acceleration to happen. And the tune is, as a bonus, seems fairly stable. So the outlook for the FFAGs, I would say, you can see that we're still at the conceptual field maps and running elementary simulations. It looks promising, but it needs a lot more study. I'm not saying they are the answer. I'm saying they shouldn't be ruled out yet. So, conclusions, and this really is the final slide. I'm not one of those who have 6 slides of conclusions. Cyclic accelerators, cyclotrons or FFAGs, are a possible solution to the ADSR. You can make a cyclic 1 GeV of order high-power machine. They are going to be cheaper, I would say much cheaper than Linux, and maybe we can even afford to have several accelerators on one power station. There are several designs at work from different groups. I've talked about 2 of them. Pierre talked about more. Stay tuned. Don't write them off. See what we come up with in the future. Thank you.
So, thank you, Roger, for this very entertaining presentation. I'm sure there are some questions. Please, you have a microphone for him.
Well, I don't have any question. I just want to make a comment about the reliability question which has been talked about in the last 2 or 3 presentations. To me, it looks that since the ADS systems can be used for power production, they can also be used along with power production for transmutation and such other purposes. So I think as a first step, we should aim at a kind of a symbiotic combination of fission reactors for the larger purpose of power production, of course, using thorium fuel cycle, and then back them up with ADS system, which perhaps will be able to do even better job as far as transmutation or destroying the unwanted materials is concerned. We can use this in energy amplifier mode so that you do recover or maybe more than recover electricity. But if we do it in that mode, and if we are talking about somewhat smaller energy amplifiers and the larger power coming, or larger systems to deliver power from fission reactors, then this reliability question would not be as severe or as demanding as one would have for a normal commercial power plant. And I think that will be a good way to make progress. Just a comment. Thank you.
Thank you. I would agree that it could be a useful intermediate step, but even a nuclear waste disposal system has got reliability requirements, as Hamid knows, well above what we've achieved today.
Yes, but reliability requirements of a chemical plant and reliability requirement of an electricity producing central electricity generating system are 2 different things, and that's the advantage that we should.
Yep.
Okay. There's another question by Hamid. Would you? Okay. Okay, so here's another question first.
I wanted to just ask if you have any comments on the fact that different reactors would have different requirements on the accelerators. For example, a molten salt accelerator would get around the question of fuel fatigue, and there are probably other things that would make the requirements of certainly reliability, but also power requirements and so on different. As just commented, for example, if you used your reactor to produce process heat rather than electricity, you would have different requirements for even longer-term availability questions.
It's a vague target, but 1 GeV is there as a fairly firm number. We want megawatts or tens of megawatts, and we want reliability, which is much better than we have today. And beyond that, there will be variations in detail, yeah.
No, the simple one about the fuel fatigue. The question of molten salt, for example, the questions of solid fuel having fatigue problem for trips is more or less.
You've still got the problem of the window.
The window can be spread out. There are all kinds of things that are different.
Okay, he wants to comment on that?
It's a... That's all right. Oh, okay, sorry. It's a comment about this issue of the reliability. It's not simply, indeed, like here pointed out, that we don't have any structure that can suffer, I would say, thermal stresses, so we can afford more. But you are operating a reactor. Is it subcritical or not? It doesn't change. And you will have working procedures to operate that reactor. And so, what we were saying, whenever we go to these longer beam trips than 3 seconds, I am just as a classical reactor operator having a scrum of my reactor. And so a scrum of reactor, if you go beyond a given time to restart, it can take you few days, if not weeks, to restart. So therefore, if my system, due to the accelerator, is shutting down, just take 100 times a year, and every restart I need 1 week. So I need 100 weeks in a year, which is only 52 weeks to operate my machine. So I can't operate it. This is the concern. It's not simply the structural effect or the fatigue on my structures. This is another aspect that we have to keep with us. We are operating reactors, even if they are subcritical.
Thank you.
I think Francois had a question.
Yeah, Francois?
Okay, I was just willing to add to your presentation that there has been an experimental demonstration of CW acceleration in scaling FFAG, the electron prototype a year ago. So going to high power protons is a matter of scaling up.